All right. Hello, everyone. It is now 3:01, so I guess we can begin the USACO Bronze final class, which will be over graphs. I hope you guys, well, if you stayed for Sage's class, I hope you guys had a fun time like watching Sage read over people's stories and critique. And hopefully you have just as much fun learning about graphs in coding and how you can sort of deal with them in USACO Bronze. So again, all the handouts for this class have been posted in this Google Classroom. If you have not joined yet, I will once again provide the link. Let me find the link real quick. Here it is, and I'll post it in the chat. All right. If you have not joined the Google Classroom yet for all the handouts, then you can find the link in the chat where the fourth handout over graphs has been posted. And I mean, since it's already 3:02, I guess we might as well get started with what I believe to be one of the most difficult types of problems in USACO Bronze. So if you're a bit confused at certain points throughout the lecture, then please don't hesitate to ask questions. And also don't be worried if like you think some of the problems are really hard, because graphs are definitely one of the hardest subjects to master in the USACO Bronze level. So, I mean, let's get started. Yes. And this is, in fact, the last week. So hopefully you guys have had a fun journey learning about USACO Bronze and stuff. So the first thing is what entails a graph problem? So most of the time, a graph problem will generally be some sort of problem that relies on manipulation inside of the coordinate plane. For example, they might ask us to identify triangles where they give us like some set of coordinates and they want us to find the number of triangles that we can form. Or on the other hand, they might give us some set of coordinates and want us to find the area that is like bounded by those coordinates. But either way, what all of these problems have in common is that they all have graphs. And I'm not entirely sure if everyone here has learned about what graphs are in their school math course, but if you have, then that's good. Give me a second, actually. Okay. Yeah. So as you can see, this is an example of a graph where every single point has both an x and a y coordinate, and you can identify any point in the plane through that x and y coordinate. Now, dealing with graphs is one of the hardest parts of USACO Bronze, not necessarily because people are unable to solve the problem, but just because most problems deal with numbers in one dimension. So having to suddenly think in two dimensions and having to put points in random places in space, like this really catches a lot of people off guard. And a lot of times graph problems can be annoying to implement or think about as a result. So, I mean, that's why we're here, learning about graph problems. And because the implementation can sometimes be a bit difficult, I've attached a few useful tips regarding the implementation of graph problems below. So let's quickly go through these. So the first tip I have is that if we want to check if two lines are parallel, which can be helpful in certain problems, then all we have to do is calculate both of their slopes and see if they're equal. So for example, if we have two lines connecting x1, y1 and x2, y2, and x3, y3 and x4, y4, then they are parallel if and only if this equation holds. Now, if you haven't seen this equation before, this is the formula for the slope of a line. So for example, let's say that, so for example, if we wanted to find the slope of this line, then why is this not working? If we wanted to find the slope of that line, then what we would do is we would find the difference of the y coordinates, which is this, find the difference of the x coordinates, which is this length, and then divide them. So the slope of this line would equal this length divided by this length. And if this is equal for two sets of 2 points, then the lines created by those points will be parallel. Something else that we often have to check is if 2 points lie in the same horizontal or vertical line. And in order to do this, we just have to check if their x and y coordinates are equal. So for example, let's say we have a coordinate plane. For example, in the coordinate plane, let's say this is a coordinate plane. I'll just erase this from before. If this is a coordinate plane and we have 2 points like here and here, and we want to know if they lie on the same vertical line, then all we have to do is look at their x and y coordinates. For example, this might be 3, 5. This might be 3, 2. But as you can see, because they actually have the same x coordinate, this means that they do in fact lie on the same vertical line. And similar logic can be applied for if they have the same y coordinate, and we want to see if they lie on the same horizontal line. So that's another useful trick that you can use. And as you can see here, x1, y1, and x2, y2, we can check if x1 equals x2 or y1 equals y2 to determine if this is true. And yeah, you can sort of just put this into an if statement or whatever you want to do with it and do some manipulation inside. The final trick that I will show you the final math implementation trick I'll show you that is useful for graphs is finding the area of a rectangle, which tends to show up quite a bit. And this does actually show up in one of our examples that's coming up. So yeah. So how this one works is if we are given the x and y coordinates of a rectangle, so that is parallel to the x and y axes. So for example, let's say that this is our coordinate plane, and then we have a rectangle that lies in here that's parallel, like let's say this. See, this side and this side are parallel to the y-axis, while this side and this side are parallel to the x-axis. So although it might be really easy for us to like find the area of this rectangle normally, because I mean, area of a rectangle is just base times height, right? It isn't exactly super simple to do with code. So lots of times, the problem statement will give us the coordinates of, for example, the top right corner and the top left corner, which are generally enough to determine a unique rectangle. So if we say that this is like x1, if this is like x1, y1, and the coordinates of the other points are x2, y2, as follows, then this is really good because this actually allows us to find both the base and the height. So if we want to go about finding the height first, the way we could do this is by noticing that this length right here is actually equal to the difference of the x coordinates, because this x coordinate corresponds to this point right here, and this x coordinate corresponds to this point right here. So if we take the difference between this length and this length, we actually end up getting exactly what we want, which is the base of the rectangle. So that's nice. And we can similarly get that the difference between the y coordinates is equal to the height. So in the end, the area of this rectangle is just going to be equal to x1 minus x2 times y1 minus y2. And this is a really handy formula that is used quite a lot in USACO graphing problems, especially when we need to find the area of a rectangle. All right, nice. So before we move on to the next section, does anyone have any questions? Dennis, do you have a question? If so, you can type it in the chat or the Q&A because you have your hand raised right now. If not, then okay. Well, if you still have a question after a while, then you can just put it in the chat or the Q&A, and I'll get to it eventually. But for now, let's move on to the next section, which is talking about a few more implementation tips regarding graph problems. So a lot of the times, since we're working in 2 dimensions, the problem statement will give us a list of points that we have to store somewhere. So for example, they might tell us like, oh, you need to keep track of the point -1, 2, and you need to keep track of the points -1, -3, or something like this, you know? And whenever we're keeping track of these points, the problem is that we can no longer just insert them into an array or array list because, well, there's now 2 different coordinates that we have to keep track of, the -1 and the 2, and then the -1 and the -3. So this is problematic. So as a result, we're generally going to have to use a 2-dimensional array or array list in order to keep track of both coordinates at once. And we'll get into how to do this when we get to example 2, which is Academia 3. Yeah, we'll get to that eventually. There's also a lot of problems where we have to do something where we're checking if certain points are neighbors. So I will redraw the coordinate grid because this is getting very messy. But let's say that, again, we have a coordinate grid like this. And then, for example, like if this point right here was 1, 1, and this point is like 1, 2, then a lot of times we might have to be like, oh, well, if this point satisfies some property, then do its neighbors satisfy some property as well, like these points? Basically, the points adjacent to a point. And this is generally handled by, because, for example, if that point is represented by the coordinate system x comma y, then we can actually get the coordinates of its neighbors as x plus 1 comma y, x minus 1 comma y, x comma y minus 1, and x comma y plus 1, as shown here. And this will, again, become useful in the second example, which might make things clearer if you're still just a bit confused. And now let's get on to the last tip before we start moving on to examples. The last tip is that a common error in graph problems is to go out of bounds. And I guess what I really mean by this is sometimes they'll give us like a grid of points. For example, they might say, oh, you want to look at all points within this specific section of the grid. Like as you can see, this is a 3x4 set of points. And something we have to be careful of is when we're like looping through our array and going through all of these points, we have to make sure we don't accidentally try and look at this point right here because this point doesn't exist. We have to make sure we don't accidentally look at this point because this point doesn't exist either. So we're going to have, sometimes we'll have to add extra restrictions just to make sure we stay in bound of whatever the given set of points is. And yeah, that's the final implementation tip. So we are now going to proceed to the examples. And before we do so, I would once again like to ask if anyone has any questions. All right, well, it appears not. So if, without further ado, let's get on to the first example question, which hopefully everyone will find decently interesting to think about. So as you can see, the problem is blocked billboard 2, and the link to the problem statement is found here. And you can click on this link by yourself if you have the handout open, but I'll also open the USACO link so that you guys can all see. So here's the statement, and I'll give you guys 4 or so minutes to read the problem, think about possible ways to do it, do the sample case out yourself, that sort of thing, before we move on to motivating the solution and coding it out ourselves. So I'll see you guys in about 4 minutes at 3:18 Central Time. Oh, and if you have any questions at this point, then feel free to put it into the chat or the Q&A. All right, it is now 3:18. So let's get on with first looking at how, like, just sort of making sure we understand how the problem works by looking at the given sample case. So let's first, as always, draw out the sample case on a grid. I guess we can use black coordinate axes because why not? Black is a good color. This, and then we can use our rectangle tool. There is a rectangle tool. Here we go. All right. So the first billboard, it tells us has one coordinate at 2, 1. So let's label that point. It has one point at 2, 1. So 2, 1. And the second coordinate is at 7, 4. So 7, 4 would be somewhere around here, we can say. So then when we draw this in, this is now the shape of our billboard, of the first billboard. So we are also given 2 more coordinates. 5, -1 is the lower left corner of the second billboard, and 10, 3 is the upper right corner of the second billboard. So let's label these points, 5, -1 and 10, 3. So 5, -1 would probably be around here, I suppose. We can call this 5, -1. And then 10, 3 looks to be around here-ish. You know, close enough. So this, we can say that this point is 10, 3. And once more, we will label it with a rectangle. Actually, we might as well label this with a different color rectangle with a fill. Let's say blue. All right, so now what the problem is asking us to do is find the biggest rectangle that we need in order to fully cover the purple rectangle. So as you can see, this second rectangle right here, which is covered in black and white, is already partially covering the purple rectangle. However, the problem wants us to find the minimum area that we need, that a rectangle needs to be in order to fully cover this rectangle. So let's think about how we might do this, right? So if we try doing a rectangle that looks like this, well, unfortunately, it doesn't seem like this is sufficient to cover the full rectangle. We still have a part that's sticking out. And honestly, no matter what we try, it seems that it's pretty hard to cover the entire rectangle unless the tarp that we draw fully covers the area of the old rectangle, like this. So because this is true, and the tarp that we create in order to fully cover the billboard must equal the area of the original rectangle, then all we have to do in order to get the answer to the sample case is find the area of the original rectangle, which, as we showed above, can just be found by subtracting the 2 x coordinates and multiplying by the difference of the 2 y coordinates. So in particular, in this sample case, we can see that this length would be 7 - 2, or 5. And then this length would be 4 - 1, or 3. So in the end, the area of the tarp we have to create is equal to 3 times 5, which is equal to 15. And that's how we get the sample case done. All right, nice. So now we have some sort of idea of how to approach the problem at least. But how are we going to solve this? Well, doing out this sample case sort of makes us think, right? Because even with this rectangle blocking part of the purple rectangle, we still had to make our tarp cover the entirety of the purple rectangle in order for it to be fully covered. So the question we're really asking here is when does this second rectangle actually affect how large our tarp has to be? And the answer to this is that it actually depends on the number of vertices that this purple rectangle has that are inside this black rectangle. And to show you what I mean, let's look at a few cases, right? So in the first case, let's say that we have a purple rectangle, and let's say that all 4 vertices of the purple rectangle are located within the black rectangle, like this. Well, I mean, obviously, since all four vertices are inside of the blocking rectangle, then the purple rectangle will be fully covered because all four of its vertices are covered. So as a result, the tarp we create will not have to actually have any area. So we can output an answer of 0. The next case that we have to consider is what happens if the purple rectangle has 3 of its vertices covered. So let's say we try to draw a rectangle that covers exactly 3 of this purple rectangle's vertices. But unfortunately, no matter how we try to do it, we can't actually draw a rectangle that covers exactly 3 of these vertices. And as you can see, it is not possible to do this without covering all 4 vertices or only covering 2 vertices. So that is unfortunate. Now let's look at the next case, which is what happens when exactly 2 vertices of the purple rectangle are covered by the second billboard. Well, when this happens, we see that the part of the purple rectangle that the tarp has to cover is now this region, because the region over here is already covered. So that's good, but how are we going to be able to find the area of this region? Well, luckily, we can do similarly as we did before, and we can first find the area of the purple rectangle, which is very easy to do. We can just use the formula from before, and then we can find the area of the overlap of the 2 billboards and subtract that. Once we've done that, we can find the area of the still uncovered part of the billboard that the tarp we create needs to cover. That's the 2 vertice case. And lastly, let's consider the 1 or 0 vertex case. So obviously, if none of the vertices of the purple rectangle lie inside the blocking billboard, then the blocking billboard doesn't do a very good job at blocking the purple rectangle. So in other words, nothing's going to happen because, yeah, the blocking billboard is not covering the purple billboard at all. So in the case where the blocking billboard covers 0 of the purple rectangle's vertices, the tarp we create will need to cover the entirety of the purple rectangle. Now, the last case is, but now what happens if the blocking billboard covers exactly 1 of the purple rectangle's vertices, as in this case, the sample case? Once again, no matter how we try to create our rectangle, the tarp that we want to cover the purple rectangle, we realize that it's actually impossible to create a tarp that covers the purple rectangle unless it covers like the entirety of the purple rectangle like this. So this means that the tarp cannot just cover some small part of the purple rectangle, because no matter what we do, there'll always be another part sticking out. And although this is hard, this might be like hard to prove rigorously, but after doing out a lot of examples, you can sort of intuitively, sort of believe that it's intuitively true. So again, if the blocking rectangle, as shown here, is covering exactly 1 of the purple rectangle's vertices, and this is the vertice, this is the vertex the blocking billboard is covering, and in order to cover the whole purple rectangle, our tarp must have the same area as the purple rectangle, because it just has to like cover like this. There's no other way to do it. All right, so now let's get started with the implementation of the solution. And again, if you're confused and didn't like understand some part of the explanation, then I have tried my best to write out all of the cases in the handout right here. So again, if you have questions, then hopefully you will be able to look at the handout, which might give a slightly better explanation than whatever I said out loud. But hopefully you are still understanding. So let's move on to how we might implement this in code. All right, so the first thing we have to do is read in the information that we're given. So in the information that we're given, we can see that we're given first a set of 4 points, and then we're given another set of 4 points. So let's read these in, right? So let's say first we're going to be reading in billboard 1. So we know that the first 4 integers represent the x and y coordinates of the lower left corner of the first billboard, and then the upper right corner of the first billboard. So x1 would be the first integer. So we can do something like this. We know that the next integer will be the y coordinate. So we can again do this. And then the next 2 integers will just be the x and y coordinates of the upper corner. So can do this. So this is the upper right corner. These are the coordinates of the lower left corner. Oh, shoot. I must have forgotten to share my entire screen again because I am a complete bot. Thank you so much for catching that, by the way. That would have been very bad if I went through the entire thing without sharing my screen. Okay, here we go. So here, hopefully you guys can all see the code now. But yeah, so these two integers represent the lower left corner, and these two integers represent the upper right corner. So now we've successfully read in the integers for one of the billboards. And this is the billboard that we want to block. Now let's do the same for the other billboard. And luckily, copy paste allows us to be very fast about this. We can just literally copy over everything and then change these numbers to like this. So now we have also successfully read in the lower left and upper right corners of billboard 2, or the blocking billboard. All right, great. So now we're finished with the input, which is the first part of every Java problem. And now we will, oh wait, actually, I just realized I need to do this instead. Okay. So now let's get on with actually calculating this, right? So the solution we created had cases on the number of covered vertices. So how on earth are we going to like write code to check how many of billboard 1's vertices are going to be covered by billboard 2? Well, if we think about it, we actually know, I guess I'll redraw this coordinate plane again because it's getting very messy. Oh, that's not working. So we actually know that in the rectangle we are given, we are first given the lower left corner, and we are then given the upper right corner. So the rectangle looks something like this. And we are given the coordinates of this point and this point. So this point would be like x1, x2, x1, y1. And this upper point would be x2, y2. Nice. So I guess the first step would be identifying exactly where the vertices of this triangle are. So obviously, we know that one of the vertices is x1, y1, and the other one is x2, y2. But we also need to find the coordinates of these vertices if we're going to be able to check if they're inside of the other billboard. But luckily, since we know that this point lies on the same vertical line as this point and lies on the same horizontal line here as this point, we can actually get the coordinates of this point to be x1, y2. And similarly, we can get the coordinates of this point to be x2, y1. And whoa, magic. So yeah, this is an important step in solving the problem. So does anyone have any questions about how we were able to get all 4 vertices of this rectangle? All right, I guess we will move on for now. But after we have gotten the 4 vertices, which are represented by the coordinates drawn here, we now have to check if they're inside of the blocking billboard. So for example, if the blocking billboard's here, how do we tell if this point is inside of it? Because, I mean, obviously, when we draw it out on a grid, it's very easy to see that like this vertice is being covered. But we can't just draw it out on Eclipse. So how are we going to do it with code? Well, fortunately for us, there is a pretty efficient way. And the thing is, let me quickly delete the fill. But let's say that this is the outline of the blocking billboard, and we want to be able to tell if this vertex lies within it. In order to do this, we see that or I guess the reason that this vertex lies within the boundaries of this billboard is because first of all, its x coordinate is in between this line and this line. And secondly, the y coordinate here is in between this line and this line. Yes, does someone have a question? if you could type your question in the chat or the Q&A for now, then that would be easier so that I can sort of read it without having to stop. But for now, I'll keep going. And if you end up putting your question in the chat or the Q&A, then I'll take a look at it. But continuing off from where we were, we can see that we know that this line right here is represented by some x coordinates, and this line right here is represented by some y coordinate. Sorry, by another x coordinate. And we realize that this x coordinate must be in between the x coordinates of this line and this line. Similarly, this y coordinate right here must be in between this line and this line. So how do we get the coordinates of those lines? Well, once again, because we are given the bottom left corner, let's say this is like x3, y3, because we are given the bottom left corner and the upper left corner coordinates of the blocking billboard as well, we can actually identify exactly which boundaries we need to lie within. So in other words, the condition that we need to satisfy in order for a vertex to be within the billboard is x3 less than or equal to x1 is less than or equal to x4, as well as y3 is less than or equal to y3 is less than or equal to y1 is less than or equal to y4. And if you're wondering where this came from, as you can see, this is the point represented by the height y1. This is the height for y3, and this is the height for y4. So we need the height for y1 to be in between the height represented by y4 and the height represented by y3, which are these two lines. And we can say similarly for the x-axis. So that is where these two conditions come from. And all we have to do to check which vertices lie within this blocking billboard is loop through all possible pairs, is loop through all the vertices and see which ones satisfy these conditions. So let's do that now. All right, so the first thing we can do is create some, let's say that C equals 0, and this represents the number of covered vertices of billboard 1. Now we create an if statement. And this if statement will just sort of entail exactly what we have here. In particular, we can write it like this. So if x3 is less than or equal to x1, and x1 is less than or equal to x4, and we also have y3 less than or equal to y1, and y1 less than or equal to y4, then we know that the vertex x1, y1 is covered. Like this. And then, so we've now done it for one vertex, which is x1, y1, but now we need to do it for every other vertex. So we've done it for x1, y1, but we also need to do it for x1, y2, x2, y1, and x2, y2. And luckily, copy paste is our very best friend in this situation, and we don't have to type out this entire if statement again, because we can just copy this if statement 3 more times and just change the indices of the variable. So like, for example, let's say that here we want to deal with x2, y1. Here we can deal with the vertex x1, y2. And in the last case, all we have to do is change all the 1s to 2s in order to deal with the vertex x2, y2, like this. And I guess we can change them in the comments as well, in case people are a bit confused. So let's go, right? Because we've managed to now finish checking which vertices lie within the blocked billboard in a pretty short amount of time, actually, because copy paste has helped us quite a lot. So I'll give people since this is might be a bit confusing, I'll give people a bit more time to look at this and ask any questions if they have them about how this code might represent if a vertex of the original billboard is being covered by the second billboard. All right, so hopefully everyone has been able to wrap this around their heads now. And let's continue. All right, so now C tells us the number of covered vertices of billboard 1. And if you remember back in our solution revolved around checking the number of, our solution revolved in doing casework on the number of covered vertices. So let's see how we might be able to implement that casework. So the first case we will cover is if the number of covered vertices is equal to 4. And if we remember in this case, all that we had to do, because if the billboard had all 4 of its vertices covered, then the entire billboard would be covered. The tarp we create doesn't actually need to have any area, so we can just output 0. Like as so. Now let's move on to the next case. The next case we need to cover is if 3 of the vertices are covered, like this. But if you remember, back when we tried to do this, it was actually impossible to cover exactly 3 of the vertices with the billboard. So we can just leave this empty. So this case is impossible. We cannot cover exactly. All right, let's move on to the next case, which has C equals 2. Actually, let's leave this case last because I think that this case is the hardest one to understand. So let's go into the final cases, which is if C is equal to 1 or C is equal to 0. So in each of these cases, I guess I'll just draw the rectangle once more. Let's change this to purple. So when we had exactly 1 vertex of our rectangle being covered, when we had exactly 1 vertex of a rectangle being covered, oh shoot, why is this not working? Okay, there we go. So when we had one vertex of this rectangle being covered, remember that the tarp we create still had to contain the entire area of the rectangle. And obviously, we covered 0 vertices, then since no part of the billboard is covered, the tarp we create also has to cover the entirety of the area. So as a result, for either of these cases, what we're going to do is we're going to print out the area of billboard 1, because our tarp must cover the entirety of it in order for the full billboard to be covered, because there's no other way around it. So we can say like covers entirety of area of billboard 1. But of course, now this raises the question, how are we going to get the area of billboard 1? Well, luckily, if we refer back to the handout at the top, we can see that to find the area of a rectangle with upper right corner x1, y1 and bottom left corner x2, y2, we can use the formula x1 minus x2 times y1 minus y2. Great. So now, because we know that billboard 1 has lower left corner x1, y1 and upper right corner x2, y2, we can just use the formula from before and plug it in to get the area. So in this case, the area would become x2 minus x1 times y2 minus y1. And this should give us the correct answer for this case. All right, so we're almost done, except we have to deal with one last case, which is the hard case, which is what happens when exactly 2 vertices are covered. And if we recall, being able to cover 2 vertices looks something like this. So notice that having 2 vertices covers means we either have to cover like these 2 edges, or we have to cover these 2 vertices, or these 2 vertices, or these 2 vertices. And again, on paper, this is pretty easy, right? All we have to do is find the area of this section right here, which we can do by multiplying the base by the height. Unfortunately, our code can't do this very well on its own, and it especially struggles at dealing with cases. Like for example, this case where these 2 vertices are covered is different than covering these 2 vertices, and the formula might like change if we're covering these 2 instead of these 2. So that's why this step is especially difficult. Now, one way to do this would be to check exactly which vertices are covered and then do casework on that. So we could say like, oh, we could have a case where if these 2 vertices are covered, then the area formula we use to obtain this area is like something. And then if that's not true, then we check if these 2 vertices are covered and then use a different formula to find this area. Then so on and so on, do the same cases for this and do a last case for this. But luckily, there is actually a very, very slick way to find the area of the overlap between two rectangles in the coordinate plane. So let me quickly type that out. So there's actually a formula for area of overlap between two rectangles, between two overlapping rectangles. So what this means is that when we use this formula, we're able to get the overlap, or this part, the overlap between the two rectangles. And this is really helpful because now we can just find the area of the second rectangle, find the area of the first rectangle, subtract the overlap, and then we'll get the final area that our part needs to cover. So, and we already know how to find the area of the first rectangle. So how are we going to find the area of the overlap? Well, this is a pretty hard formula to prove. So I'm just going to say it outright, and then I'll try my best to like motivate where it comes from, but it's all right if you don't fully understand. So so the way this works is if we have two rectangles with bottom left, so let's say that the first rectangle, let's say rectangle 1, bottom left corner x1, y1, top right corner x2, y2. And then let's say rectangle 2 has bottom left corner x3, y3, and top right corner x4, y4. Like this. So what is the formula going to be for the overlap between these two? Well, the formula is actually going to be, I want to type this where everyone can see it. Okay, that looks good. So the formula is the maximum of x1, x3 times so minus the minimum of x2, y2, and then multiplied by the maximum of y1, y3 minus the minimum of y4 of y2, y4. This is the area of the overlap between these two rectangles. Oh, what the heck happened? Oh, whoops. Okay, I must have accidentally clicked on the link. Okay, we are back. Good. So just to show how you might be able to think of this formula. So I guess we could say, let's look at this example right here, right? So let's say that the purple rectangle has vertices x1, y1. This is the bottom left corner, and it is upper right. Actually, I'll just say, you can just look at this. The purple rectangle has bottom left corner vertices x1, y1, and upper right x2, y2. And then the gray one has bottom left corner x3, y3, and top right corner x4, y4. So how would this formula work to get the overlap? Well, first, let's find the maximum of x1 and x3, right? So as we know, this somewhere like right here, this point would be represented by x1, y1. And to find x3, we know that the bottom left corner, which is around here, so this point would be represented by x3, y3. So now, let's find. Oh wait, actually, I just realized I messed this up. It's not too bad of a mess up though. It's just I need to switch these two, and then this should give us the correct form. So let's look at where the maximum of x1, x3 is, right? Well, obviously, x1, which is right here, is larger than x3. So maximum of x1, x3 would be this point. All right. Now, where would the minimum of x2 and y2 be? Oh, I typed this wrong as well. This is supposed to be x4. I'm so smart. All right. So where would the minimum of x2 and y4 be? Well, we know that the upper left corner, which is right here, is represented by x2, y2. And we know that this upper left corner is represented by x4, y4. So as a result, the minimum of x2 and x4 would be this point right here. All right, and that is a lot of blue. So let me try to erase some of it just for the sake of clarity. Oh shoot, did not mean to do that. So essentially, we know that this point right here would be represented by, this point would have an x coordinate of maximum x1, x3, and this point would have a x coordinate of minimum x2, x4. So when we subtract these two, we actually end up getting the width of the overlapping region. And if we do out all that sort of complicated logic similarly, we can get that the height, or right here, is represented by minimum y2, y4, because this point is actually the minimum of y2, y4, and the maximum of y1, y3, which is represented by the y coordinate here. So in the end, this formula is just sort of a complicated way of saying we want to multiply the width of the overlapping region by the height of the overlapping region. And it just so happens that this formula allows us to do it in a pretty efficient way. And we don't have to deal with cases if we do this, because regardless of like which two vertices are being covered by these two rectangles, the overlapping region will still have an area of this. So let's just finish off the problem by by using this really strong formula. So we can get that area, let's say that the int area of billboard. So again, the area of the billboard would be this. Using the formula that we had from before, the area of the overlap would be represented by let me check, min x2, x4, and whenever we use min, we have to use math.min. Math.min x2, x4 minus math.max x1, x3 multiplied by math.min, oh shoot, not sure why that happened, math.min y2, y4 minus math.max, okay, I'm not sure why this is, okay, minus math.max x1, y1, y3. And this is just the formula that we had from before. And again, I think that this is a really useful formula to sort of know. It's kind of hard to derive and kind of hard to prove, but again, it's still really useful, which is why we're going to be using it. So now we have the area of the purple billboard, and we now have the area of the overlap between the blocking billboard and the original billboard. So finally, all we have to do to get the area that the tarp has to cover is to print out the difference between the two, which is the area of billboard minus the area of the overlapping region. And just like that, we have finished the final case for if two vertices are covered. So here's the 4 vertices case, 3 vertices, 2 vertices, 0 or 1. And now let's see if we have successfully covered all the cases, or if we mess something up and need to come back to check if it's wrong. So let's go to the Java. We choose our file to submit. Is this one, right? Yes, block billboards, right? Let's hope that we did not make some very strange error. Or that our logic, okay, well, we got the first test case, that's good. Got first 4, that's also good. Okay, so we probably got all of them. Yes. Okay. And as you can see, our code runs successfully on all of these cases. And yeah, that is the first example problem. Okay, I just noticed that I may have ran slightly over time going on the first example problem, because we were actually, believe it or not, we were supposed to have time to cover a second example problem, Academia 3, and this example problem was supposed to be harder than the first one. So I think I may have not kept track of time very well. But that's all right, because I mean, we went pretty in depth into blocked billboard too. So I really hope that going over this problem really helped you guys sort of understand how to deal with certain types of graph problems, at least this sort of graph problem, where you want to find the overlap between two rectangles and print out the area of rectangles. Just sort of was a decent introduction into these sorts of problems. And if you want, I highly recommend reading through the explanation that I wrote here for Academia 3. And fun fact, Academia 3 was actually also one of the example problems for greedy algorithms in handout 2 if you were in the class back then, which hopefully you were. But the reason it is also an example problem for graphs is because it is the problem also has like some graph-like techniques. And I think it's really instructional to just sort of read through and understand how to implement the graph-like structure that is used within the problem. But we don't have time, so we won't go over that specifically. But yeah, you can read over this explanation later. And the Java code is attached here, which I can confirm does actually get all of these test cases correct. And lastly, here are 3 really good practice problems. We're dealing with graphs. Blocked billboard. Yeah, if you noticed, the first problem was blocked billboard too. So this is the original blocked billboard. There's also bucket brigade and stuck in a rut. So all 3 of these problems, really instructional. Highly recommend that you try to solve them by yourself if you want to become more familiar with graph problems. And if I'm thinking about it, I think that USACO Bronze has recently had a few more graph problems than normal. Like I think in the 2020 to 2021 USACO season, they had 2 graph problems in total, although I'm not sure if they had any in 2019 and 2018. So maybe they won't come in 2021 and above, but then again, it never hurts to be safe. So before we go, I also want to introduce a few more resources that you might be able to use to improve your coding, your coding abilities that I think are really useful. So the first one I want to show you is usaco.guide. And the reason usaco.guide is so helpful is because it's created by like a lot of people who are really good at programming, and they have like detailed sections for all levels of USACO programming. And if you want to continue your USACO journey, then this is definitely a place that you will be able to get better at. I guess I'll type the links to everything in the chat because the second one is called codeforces.com. And this one is just really good for practicing in contest coding. So I didn't discover this until really late on, but I think that codeforces.com is really fun in the sense that, first of all, the contests are a lot more frequent than USACO. Like USACO, there's 4 contests a year, but Codeforces has a lot more contests every year. And as a result, you have a lot more chances to like practice your coding ability and stuff. Secondly, a lot of the problems can be like, some of the problems are like a bit more approachable than that of USACO Bronze. So if you're struggling on USACO Bronze, then maybe try the first few problems of Codeforces. I'm not entirely sure. And lastly, what I really like about Codeforces is that they really gamify like they really gamify the problem solving system. So as you can see, everyone here gets a certain amount of points for solving each problem in a certain amount of time. And this makes it pretty fun because you can be like, oh, I have more points than this other guy and stuff like that, and you can see yourself on the leaderboard, which is pretty interesting. So yeah, those are the main 2 resources I wanted to share with you. And yeah, I mean, I can't believe it, but we managed to make it through 4 weeks, guys. 4 weeks of USACO Bronze coding. I hope you guys really learned a lot, just as much as I did, because I'm going to be honest, making these handouts was pretty difficult for me because I had to spend a lot of time going through all the old USACO Bronze problems. But I will admit, it was fun. And yeah, I got to be able to teach all this stuff, which is pretty cool. Hopefully you guys learned a lot. Yeah. And I guess one final thing before we go is that we at Kid Teach Kid would really appreciate it if you guys could go to Google, search up Kid Teach Kid like this. And then if you go here, you can see that on the side, it says Kid Teach Kid, 1 Google review, this stuff. There's a place where you can write a review if you appreciated what we did at Kid Teach Kid and you want to just let us know what we did well, let us know what we did badly. You can click on write a review as shown here. You can rate us however many stars that you think we did. And hopefully, you think that I was a 5-star teacher, but don't worry, I won't be offended if you don't. Okay, maybe a little, but again, it's up to you. So you can rate us some number of stars and then just share a couple of details about your learning experience at Kid Teach Kid and that sort of stuff. And again, we would really appreciate it if you could go to Google and just sort of let us know what you thought of our classes. And yeah, there's 2 minutes left. So I guess I'll give you some time to hopefully write a review on Google. So let us know what you think. And I guess we will now wait for Andy, where Andy will be teaching some USACO Silver concepts. And if you're interested in that, then you should definitely stay because this is his last class. And I'm 100% sure that he is teaching something very interesting. So yeah, thanks so much, guys.